Hi, we have one more little couple of pile of things to talk about with confidence intervals. This is video 3. Okay, so first video is all about the theory and why we use confidence intervals and the general idea. Okay, second video was actually going through all the steps of panic about constructing a confidence interval and interpreting a confidence interval. And today we're just going to catch a couple other things that sort of deal with this. So, first off, when we are talking about a confidence interval, remember that the formula says that we have a point estimate or statistic plus or minus the critical value times the standard error of the statistic. That product, critical value times standard error of the statistic, is referred to as the margin of error. The margin of error is how much you're going up and down away from your estimate, away from your statistic. So when we're talking about margin of error, you could say margin of error equals the critical value times the standard error. Or for a single proportion, we're talking about a z for the normal distribution times the standard error, which is the standard deviation formula with that p hat used instead of p because we don't know what p is. Now, the good thing about this formula is that you can actually rearrange this formula to solve for n. So if you started off the problem and you knew what degree of accuracy you wanted, you want to predict the proportion of people who support the governor within 5% of the truth, you could actually get within 5% of the truth or within 10% of the truth or within a certain margin of error by working backwards and solving this. So here's how we would go through that process. So for example, okay, in a previous study, we estimated that p hat was 75%. Suppose we want to know how big of a sample we would need to be 95% confident that we would be within 0.05 of our true population proportion. Now, this idea of within, that's that margin of error, plus or minus. We want to be within plus or minus 0.05, okay? All right, so things I know from the problem, it says I need to be 95% confident. So I know since I'm dealing with a proportion, if I'm 95% confident that the z-score that goes with 95% confidence is 1.96. I also know that the margin of error is 5%. I want to be within 5%. So that number I can pick out from the problem. And I know that the p-hat value from a previous study is 75%. So we think maybe it's different than it used to be, but 75%, we hope that's pretty close to what it is now. All right, so I'm going to take this formula up here and I'm going to directly sub into it. So the margin of error is the 0.05. Okay, so notice I'm not using the whole confidence interval part, just the margin of error part. I know the margin of error is equal to the z, 1.96, times the square root of my p-hat estimate, 0.75, times the 1 minus p-hat, which is 0.25, divided by n. And now I need to solve this. Now, if you're going to solve this by using your calculator or algebra skills, again, you would divide by 1.96, then you'd square both sides, multiply by n, divide by the answer result. I mean, you could solve this using algebra, no problem. If you feel uncomfortable solving for that, don't worry, because you got your TI Inspire. You could always use that solve command on there. Remember, that's menu algebra solve. So press menu algebra solve in the scratch pad. You're going to type in 0.05 equals 1.96 times the square root of 0.75 times 0.25 divided by n. And just remember that in order to get this to work, you have to press comma and then the variable that you typed in, whatever you typed down there, you need to be inside the parenthesis, but you need to be outside the radical for that to work. And I end up with 288.12. All right, so here's the issue with that. 288.12, that is the minimum size. The minimum size that this could be, because we want to be within 5%. So what I'm going to need to do is, I know two things. First is that n has to be a whole number because n is a sample size. You cannot have 0.12 of a person. You can't, you can't. So n has to be a whole number, just like x, the number of successes, has to be a whole number. Okay, these are whole number counting values. We're not allowed to have a decimal for n. So it needs to be a whole number, but I also need to round it up, not because it's closer to that, but because the way sample size and margin of error work. If I round n up, it's going to make the standard deviation go down, and it's going to make the margin of error slightly smaller than 5% where we set it. If I take n and I round it down, it's going to cause my standard deviation to go up, and it's going to make my margin of error slightly larger than 5%. And remember, we want to be within 5%. So for these sample sizes, if you're trying to stay within a certain margin of error, to be on the safe side, you're always going to round your sample size up to that nearest whole number. All right, so here's another one. How big of a sample is needed to be 95% confident that we will be within 2% of the true population proportion? Now, the 90%, that may not be one you have memorized. So remember, if you want to figure out what the z-score for 90% is, you could draw yourself a little curve. There's 90% on the inside, leaving me 5% to the left, another 5% over here. You could do an inverse normal and get z as negative 1.645. The other thing you could do is use that t-table and look at the bottom for the confidence level, look up at 90%, and you're going to get that 1.645. The other thing that we know from this problem is that the margin of error is 2% because it says we need to be within 2%. However, we do not know p hat. The last question, it told us what p hat used to be, or what we thought p hat used to be. We don't know that now. So what we're going to do is that any time that you don't have a p hat value or a guess for p, you're going to approximate it at 50%. Okay, so we're just going to 50%. That's called a very conservative estimate. A very conservative estimate is use 50% in that spot. Okay, so you're just going to guess that as it goes in there. So I'm going to set this up. Margin of error is 2% equals 1.645. That is my z-score times the square root of p hat times 1 minus p hat over n. In this case, that's going to be 50% times 50% over n. When I solve this, and again, you could use that solve in your calculator for this if you wanted to, or algebra, I get 1691.2. So again, n has to be a whole number, but what we want to do is we want to round up. And I still have the same graphic from the last problem, but we want to keep the margin of error under that 2%. If we round down, it's going to make the standard deviation go up. And if the standard deviation goes up, then that's going to affect that margin of error and make it larger than what we want it to be. Okay. All right. So we're going to use n equals 1692. All right. So again, the idea with confidence intervals, when we're talking about this margin of error, is that the confidence level C, that confidence level, like the 90% and the 95%, etc., what we're saying is that's sort of an overall success rate for the process. So that means if we were to take all possible samples of size n, and we were to construct a confidence interval based on the p hat value from that, we would end up that about C% of those confidence intervals would capture the truth. So I have mu here for a mean, but I want you to imagine that we found a sample and we constructed a confidence interval here, and the truth is running along that line. So a 95% confidence interval, what we would expect that about 19 out of every 20 samples, about 95% of all samples that you take, if you were to construct a confidence interval from those, 19 out of the 20 would successfully capture the true population. Now, the parameters. So it may be really close to the edge, like in some of the Price is Right game, or it could be right in the middle. But we would expect to actually miss it about 5% of the time. So it wouldn't be unusual for about 1 of the 20 samples to miss and to not win. All right, but basically what we can see here is that the more confident you are, the less accurate your interval is going to be. Now, when I'm talking about accuracy, I'm talking about how close you are to what you were trying to do. So my accuracy means I've got a small margin of error. I've got a very accurate, a very small window, okay, as opposed to being correct. Being correct is that confidence level. Okay, so again, if we made these intervals wider, if they were wider, we would be more confident, but because they're wider, we don't have nearly as good a guess about what they're going to be. Now remember, again, we're not guaranteed to win the trip to Rome. But there are a lot of things that we can do to make ourselves more confident and deal with this. So the margin of error has this form. Again, margin of error is critical value times the standard error of the statistic. It's that after the plus or minus part. So the critical value, that's that z, that's affected by the confidence level. So the larger your confidence level is, the farther out from 0 you have to go with your z-score. That gives you a larger z-score for the formula. So the more confident you are, the larger your margin of error is, so the wider your interval is going to be. So a greater level of confidence is a less accurate prediction. Okay. Oh, it's between -40 and 200 above for the high temperature for the day. I mean, it's going to give us a less accurate guess to what we're doing. So the other side of that is that if you have a lower level of confidence, that means you don't have to trap as much of the curve. Your z-score is going to be closer to 0. That's going to give you a smaller z-score, which is a smaller margin of error. The other part of this formula is that standard error of the statistics. So again, confidence level, okay, is based on a wider, more confident, wider interval. Okay, the standard error, the thing that affects that more than anything else is the sample size. So a larger sample size gives you a smaller standard deviation. And if that smaller standard deviation or smaller standard error there that we're going to use, that's going to make the margin of error smaller. And a larger sample size, or sorry, a smaller sample size is going to make the standard error larger, and it's going to give you a larger margin of error. So if you increase your sample size, it makes your standard error smaller, which makes your margin of error smaller, which makes you more accurate with your guess, closer to the truth. Less margin of error. And if you increase your sample size, again, smaller standard deviation. The other way works too. If I decrease my sample size, it's going to increase my standard error or my standard deviation. It's going to increase my margin of error, and it's going to make my guess less accurate. Okay, so to increase your accuracy, and by accuracy we're talking about margin of error. I want to make my margin of error smaller. I want to make the variability smaller. I want to get closer to the truth. You either have to lower your confidence level or you have to increase your sample size. Okay, those are the only two things that will shorten your confidence interval and decrease your margin of error. All right, so I have an example here. It says a random sample of 1,000 American women was selected, and the proportion reported having a physical in the last year was determined. A 99% confidence interval was constructed and was found to be 0.65 to 0.76. What was the point estimate, or the statistic? What was the margin of error? Okay, so one thing to think about, this confidence interval, that's the lower bound to the upper bound. Okay, the statistics should be right in the middle, and then the margin of error is how much you go up and down to get those endpoints. So if you're looking for the midpoint of 2 points, you could find the arithmetic average. Okay, so we have 0.65 plus 0.76 divided by 2 gives me a midpoint of 0.705. 0.705. And if you wanted to find the margin of error, I need to know, well, how far away from 0.76 is 0.705, or you could use the 0.65. We get a margin of error of 0.055. And you could double check. 0.705 plus 0.055 should give you 0.76. 0.705 minus 0.055 should give you 0.65. Okay. Now, there is another thing you can think about too. The confidence interval is basically 2 margin of error distances, because it's up 1 margin of error and down 1 margin of error. So if you know what the margin of error is, if you know what the width of the confidence interval is, that's 2 margins of error. So 0.76 minus 0.65, it's 11% wide. So divide that by 2, that would give you your margin of error of 0.055. So you could take your 0.76 minus 0.055 to work backwards to get that 0.705. Okay, now consider what would happen if you take a sample of size 250 and find the same point estimate. So the same point estimate, the same 0.705. What would happen to the width of the confidence interval? All right, so we know that we started off with 1,000. And so now we're saying, what if we got 250 and everything else stays the same? So if I decrease the n, I know that I'm going to increase my standard error. Okay, make the denominator smaller, makes the fraction larger. And if I increase my standard error, it's going to make my confidence interval wider. So that would be the first part of this. It's going to be wider, but we can actually be a little bit more specific than just wider. So let's see if we can figure this out. So the standard error itself, I'm going to use the 0.705 estimate here. If that's the same for both of them, but the first one used 1,000 and the second one used 250, I get 0.14 for the first, and I get 0.028 for the second. So I can actually see it's not just wider, but it's twice as wide. Everything else is still the same, but we went from 0.014 to 0.028. So the width is going to increase by a factor of 2. It's going to be twice as wide as it was before. So there's this relationship between confidence intervals and the sample size, and it's kind of like an inverse square root. Okay, so if you notice, the only thing different about these two formulas, the numerators were the same, and then 1,000 is 4 times 250, is that the first one had a 4 in the denominator. So this guy over here is 1/4 of the original size. And since that's square rooted, Okay, it's like a 1/2 is that proportion. Okay, so what happens is overall it makes it 2 times as wide. Okay, so it's inversely proportional to the square root of n. That means that if I take and I multiply my sample size by 1,000, so I started off and I took a sample size of 3, and then I took a sample size of 1,000, then my if I go bigger on the sample size, the square root of 1,000 is going to be the fraction of that. Okay, so it's going to be reciprocal. So it's going to change that. So if you make your sample size bigger, your confidence interval gets smaller by the square root of that factor. Okay, if you make your sample size smaller, your confidence interval gets bigger by the square root of that factor. So in our case, we went smaller by a factor of 4, which makes our margin of error get bigger by a factor of 2, because that's that square root. All right. So as far as confidence intervals go, you need to be able to interpret not only the confidence interval itself, which is the from here to here, but also the confidence level, which is the 90%, 95. These are two different interpretations. You got to be able to talk about both of them. So a confidence interval is basically fill in the blank. We are C% confident that the interval from here to here captures the true parameter in context. The confidence level is that 95%, 90%, etc. And basically what we're saying there is that if I were to repeatedly take samples of size n, what I'm expecting is about C% of the confidence intervals I would make from those samples would capture the truth. Okay, so for example, in a random sample of 317 teens, 117 said yes when asked if they included false information on their profile. My nephew has a Facebook page that says he's employed at the Krusty Krab, so that kind of thing. So a 95% confidence interval for the proportion of teens who use false information on their profile is 0.32 to 0.42. Okay, so we've got our confidence interval, 95% confident. All right, and I have a question. It says, interpret the confidence interval and the confidence level. So just to be specific here, the confidence interval is the actual interval of values. The confidence level is that 95%. All right, so here we go. For the confidence interval, we would say, I am 95% confident that the true proportion of teens who used false information or who said yes is captured by 0.32 to 0.42. So the confidence interval, how confident are you? True population parameter in context between those two values. The confidence level is the 95%. Now the thing about the 95%, it has nothing to do with this 0.32 and 0.42. Okay, that is one specific instance. The confidence level, we're talking about what does 95% mean in general. Okay, so the confidence interval says if we repeatedly take random samples of the same size, so we took 317, so 317, if we repeatedly take samples of size 317, if I repeatedly drop 100 Hershey Kisses, we would expect about 95% of the confidence intervals that we made from those samples to capture the true proportion of teens who said yes. Okay, so this is not a probability. It's not a chance. You should never, ever, ever pick any answer or write anything about a chance or a probability. What we're saying is if we repeatedly do this, we expect success in about 95% of those confidence intervals we construct. Okay, follow-up question. Does the confidence interval, that's the 0.32 to 0.42, support the claim that a majority of teens use false information on their profile? Now, this goes from 0.32 to 0.42. That is less than 50%, so not really. A majority means that the true proportion needs to be bigger than 50%, so no. The entire confidence interval is less than 50%, so it's not plausible that a majority said yes. Okay, what about 40%? Does the confidence interval support the claim that 40% of teens use false information? Now, the catch of this is that 40% is in this interval. All right, but I don't know if 40% is the right number. It could be 33 or 41.5 or anything in that interval. So what about 40%? It is in there. So the confidence interval includes 40%. So it's plausible that it could be the true proportion. Now you want to be really weaselly on this. Basically, here's the idea. If your confidence interval does not include the suspected value, then we're saying we don't believe it's plausible. not going to be plausible. But if your confidence interval includes a suspected value, basically you don't have enough evidence to say that it's not true. It's in there. It could be true. Plausible. Okay, but you really can't say it is true either. I can't say that it is true. I can just say that it's plausible that it could be. Okay. So you kind of have to be a little bit Weasley, but it's in there, but that doesn't mean that's the right answer. It's one of the possible right answers. Okay, now a couple things you need to be able to do in this chapter. Okay, so first off, you've got to be able to construct and interpret a confidence interval. You should be able to do that using a formula, and you need to be able to run it on your TI Inspire. Okay, so both of those, the formula setup and the TI Inspire. Okay, you need to be able to complete all the steps of panic properly, which means you need to be able to check those assumptions in detail. You got to name the test. You got to be able to write the conclusion. All those steps, you should be able to do all of those as you go through. You got to be able to find the critical value for any confidence level, which means if I say I need you to be 90% confidence or 98 or 80, whatever that percentage is, you have to be able to find that critical value of Z. Remember, you can do that using the inverse normal command on your calculator. Or you could use the table with the T on it and look at the bottom of that. You need that for the formula itself, and also just to be able to work through multiple choice questions about critical values. You need to be able to interpret a confidence level as well as the interval. So be able to say, what does it mean to be 95% confident? Okay, you need to be able to find a sample size for a specific margin of error. So if I say, well, if I want to be within 5%, how many people do I need to interview? Got to be able to deal with that number. You need to use a confidence interval to decide if a claim is plausible. So looking at this, is it plausible that it's more than 50%? Is it plausible it's 40%? Be able to use that confidence interval. And remember that the confidence interval gives you a range of plausible values for the truth. All right, so other things that you need to know, first off, remember that the Z star, those critical values, can be found on the last line of that T distribution table. If you're looking for those, you can also compute it using inverse normal on your calculator, but that may be more work than you want to put in. The confidence interval and the standard error formulas, both of those are on your AP reference sheet. Those are not things you have to have memorized, but they are things you have to be able to use. If the confidence level is not provided, always default to 95%. Okay, so if it says construct a confidence interval and nothing is said about what level of accuracy, use 95% as your default level. Okay. Sample sizes. Remember, sample sizes are n's, and approximate success counts, those are x's. Those have to be whole numbers. So you're going to round n up if you're trying to stay within that specified margin of error, because that's going to keep you within the margin of error. But for the x's, you're just going to round to the nearest whole number. Your calculator does not like it when you try to put a decimal in for x or n in any of those fields. They have to be whole numbers. Okay. If you're computing a sample size for n and there's no estimate for p or p hat provided, then use that 50%. That's that default in the standard error formula. That is considered to be a modest estimate, a reasonable, generous estimate on that. Remember that margin of error changes by an inverse square root factor of sample size. So if your sample size is 9 times bigger than the original, your margin of error will be 1/3 as large as the original margin of error, because the square root of 9 is 3 and you want to reciprocate it. So if sample size goes up, margin of error goes down. Sample size goes up by times 9, margin of error goes down by a factor of 3, so down by 1/3. Same thing if your sample size is 1/4 of the original sample size, so your sample size goes down, we would expect margin of error to go up, and it goes up by a square root factor. So if your sample size is as 1/4 the size, then square root of 4 is 2, so that means my margin of error is going to be twice as big. So there's this reciprocal square root change happening there. All right, that is it. Good luck with confidence intervals.